Well, hello and welcome to this next series that I'm going to do on algebra and number theory, a sort of journey into algebra and number theory. And just by way of introduction to this, I'm going to work through these notes. So number theory is essentially concerned with the properties of natural numbers and integers, that is with the sets n, which are the natural numbers 0, 1, 2, 3 and so on, and the set z. Z, of course, standing for the German word Zahlen, which is the word for number, or numbers in German, and it was German mathematicians that first used this symbol, and so we use Z for the set of integers, which includes the negatives. Now, number theory itself goes right back to the ancient Greeks and probably earlier. Abstract algebra, on the other hand, was developed as a means of generalizing and systematizing the underlying structures of the number systems. We'll see shortly that a ring is simply an abstraction of the set of integers. A field, we'll see, is an abstraction of the set of rational numbers, Q, and we'll see other structures that are just generalizations of these basic structures of numbers. So these notes attempt really to bring these two central parts of modern mathematics together so we can look at a variety of problems in number theory, solve and understand them using techniques and ideas from modern abstract algebra, which will in turn be motivated from the number theory. So many questions in number theory, of course, are very easy to state but very difficult to solve, and I just list a couple of examples here. The famous, of course, Goldbachs conjecture, that if we suppose we take any even natural number, say 520, the question is, can we write it as a sum of two primes? Well, in this case we can, because 520 I can write as 503 plus 17. These are both primes. A little bit more surprising is we can write it as 263 plus 257, and these two actually turn out to be primes as well. And the question then is, can every even number greater than 2 be written as the sum of two primes? And the answer is we don't know, and it's widely believed to be true, but there is no proof of it, and it's known as Goldbachs conjecture. As a second example, take another natural number, say 34. Can we write it as the sum of two squares? Well, we can, because here it is. 34 is 9 plus 25, and that's 3 squared plus 5 squared. Well, if you try doing the same for 7, you run into grief. Trial and error tells you can't write 7 as the sum of two squares. How do we explain this? How do we tell for larger numbers? If I give you some large number, how do you tell where you can't use trial and error? It takes too long. How do you tell when such a number can be written as the sum of two squares? Now, surprisingly, our method of attack on this is going to be through the complex numbers, and we will have a look at this problem later on. Third example, the very famous Fermat's last theorem, of course. There are solutions. 2x squared plus y squared is z squared. For example, the obvious 3 squared plus 4 squared is 5 squared. How do we find all solutions systematically? Are there any integers 2x, any non-positive integer solutions 2x cubed plus y cubed to z cubed? And of course the answer is no, by Fermat's last theorem, which was only proven not that long ago. You take another example, take the number 6, then you write down its Aliquot factors, that is the factors except 6 itself. So you write down 1, 2 and 3, and if you add up these three factors you get back to 6 again. Are there other numbers with this property? Well, you may know that, for example, 28 has this property. The factors of 28 are 1, 2, 4, 7 and 14. If you add them up you get back to 28 again. And how do we find such numbers, and are they of any interest to us? How many prime numbers are there is another thing we will be dealing with fairly soon, in fact. I take this number here, 3, and I raise it to this massive power, 746364732, and I divide that number, which is ginormous, by 13. What's the remainder? well. We're going to have a look at questions like that as well. On a slightly different note, we're going to have a look towards the end of this by looking at some geometrical problems, such as, can we trisect a given angle using only compass and an unmarked ruler? And you may know the answer to that is no. Can we construct, with compass and rule, a square with the same area as a given circle? So I draw a circle. Can I construct a square using only compass and rule with the same area? And you may know the answer to that is no. Can we construct an angle of 3 degrees using only compass and rule? Well, that's an interesting question. Can we construct an angle of 3 degrees using only compass and rule? And we'll examine that particular question as well. What regular polygons can we construct? Can we construct a regular pentagon using only a compass and ruler? And the answer, of course, is yes, and we'll have a look at that later. Can you do one with 7 sides? And of course the answer is no. And again, we want to see what conditions are there on these sides of these regular polygons to be able to construct them. So these are some of the things we're going to be talking about in these videos. Firstly, I want to introduce this notion of the integers and to talk about rings, what is a ring in mathematics. So you're undoubtedly familiar with the set of integers. There they are. There's Z standing for the German Zahlen. In particular, when we try and abstract off from this, we look at what we can do with this set. And we can add any two numbers in the set. I can add 2 plus 3, I get 5. It's still in the set. I can subtract. I can take 1 minus 2 is minus 1. That's still in the set. So I can add or subtract or even multiply two integers and I get an integer. It doesn't work for division, however. If I divide 3 by 2, I no longer get a whole number. So in this set, we say that this set Z is closed under addition, subtraction and multiplication. And there are lots of other sets in mathematics that have these and other properties in common with the integers. For example, if we take the set of even integers, which we're going to write as 2Z, this one is also closed. If you add 2 evens, you get an even. If you subtract 2 evens, you get an even. If you multiply 2 evens, you get an even. This set is also closed under addition, subtraction and multiplication, whereas if I take the set of odd integers, it's not closed. For example, I could take 1 plus 3, they're odd integers, add them together and I get 4, which is not odd. Are the odd numbers closed under multiplication? I leave you to have a think about that quickly. Here's another set of objects. This is called Z root 2, which consists of all numbers of the form a plus b root 2, where a and b are integers. So, for example, we might have 7 plus 3 root 2, or we might have minus 2 minus 5 root 2. So these are examples of objects that are in this set. Now, it's pretty obvious that if we can add these together in the obvious way, and this gets me something of the same shape, so this set is closed under addition and subtraction. If I take two objects in the set, multiply them together, if you expand all this out and just rearrange, you can write it like this. So you get something plus something times root 2, and that means that there's an extra bracket there we don't need. So that means this set is closed under multiplication. Now there are many other examples. We haven't got a problem sheet here. There are many other examples of sets of this type. But I'm going to formalise this idea by defining a commutative ring. So a commutative ring is a non-empty set R with some method of adding, which I'll call plus, and multiplying, which I'll call dot, the elements of R, such that for any A, B, C in this ring, it's closed under addition and it's closed under this multiplication. So I take A plus B or A dot B and they stay inside, the answer stays inside R. It satisfies the associative law of addition. So if you add A and B firstly and then add on C, you get the same as if you add B and C and then add on A. And similarly under multiplication, that's called the associative law. It's got a distributive law. You can take brackets out in the usual way and that everything works. It's got a commutative law because it's called a commutative ring. So that means A plus B is B plus A and A times B is B times A. Not all rings are commutative. We're defining here a commutative ring. Because we're dealing with number theory and the integers, everything for us is going to commute. So we'll look at commutative rings. Now there's a very special element 0 in the ring, which has the property that if you add 0 to anything, it doesn't change it. And also we need to be able to cancel, we need negatives. So if A plus X, so if given A, there is an X, so that A plus X is 0. For some X in the ring, this X is just, you think of it as just the negative of A. Now, the second axiom of part 4 is usually not included. That's what I mentioned here. This one here is normally not included in the axioms. Rings which have this property are called commutative rings. So for us, all rings will be commutative, and I'm just going to use the word rings. Some rings have an element 1, which has the property that A times 1 is A. Now the set of even numbers is a commutative ring but doesn't have a 1 in it. So such a ring is called a ring with a 1. So in example 1 above, that's the one of the even integers. This is, it's not a ring with a 1, it is a ring but not a ring with a 1. And the ring of integers is not closed under division. So minus 2 divided by 3 is not an integer. A couple of other examples you might like to play with and check that they are rings. We take the set A of all 2 by 2 matrices whose determinant is 0, then this is not a ring. You can find 2 matrices whose determinant is 0 and you can add them together and you find the determinant may not necessarily be 0. On the other hand, if we take this set, the set of all matrices of this form, where we've got A and B and minus B, where A and B are just integers, or even just real numbers in fact, then such a set of numbers is an example of a ring. Well, the little bit about the set of integers. Given integers A and B, if A divides B, or A goes into B with no remainder, then we're going to use this notation. A slash B means A divides B. This is a statement. So for example, we could say 3 is a factor of 18. 3 divides 18. Now, more formally, we say that A divides B means that B is some integer multiple of A. So it's Ka for some integer K. And I put a slash in it. We use that notation for A does not divide B. A is not a factor of B. A couple of basic little facts about this. If A divides B and B divides C, then A divides C. If A divides B and B divides A, then A and B are the same up to a sign. It's plus or minus B. And this one here is actually quite useful. It says if A is a common factor of B and C, so A divides B and A divides C, then A divides any integer linear combination of B and C that you like. So A is a factor of bx plus cy for any integers x and y. This is actually a useful little fact in number theory. I've just done a little proof of the first one, just to show you how to set these out. You should have a go at doing proofs of the others yourself. So firstly, if A divides B and B divides C, we want to show A divides C. So if A divides B, then B is some multiple of A. B divides C, then C is some multiple of B for some integer L. And I can simply substitute then the B, I can replace with AK in here. So I get C is AKL, and that means C is some number times A. So A is a factor of C. I'll leave you to prove the other bits. Now prime numbers, of course, are of great interest. So primes p whose only factors are numbers p whose only factors are plus or minus 1 plus or minus p play a very special role in number theory and in mathematics generally, and they're called primes. So definition: a positive integer p, not 1, is going to be called a prime if and only if, whenever you try and factorise it as a times b, then either a or b is plus or minus 1. That is, these numbers do not factorise in any sensible way apart from one of the factors being plus or minus 1. A non-zero integer is either plus or minus 1 or plus or minus 1 times a prime or a product of primes. And this is a very important basic fact about prime numbers and about the integers. A little proof here by contradiction. So suppose there are integers which are none of the above. So we're going to let n be 1 with the smallest positive absolute value. Now n is not prime by our assumption, so n is a times b, where a and b are integers, and a and b are not plus or minus 1. But then, of course, if that's the case, then the size of a is less than the size of n, and the size of b is less than n. And so a and b, they must be prime, or the product of primes by the minimality of n. But then, in that case, we have n is a product of primes, which is a contradiction. So finally, we can state that every integer n has a unique factorisation, plus or minus p1 to the alpha 1 up to pr to the alpha r, where pi is prime and each alpha I is a positive integer, and this is called the canonical factorisation of n. Of course, we know that the number of primes is infinite, and here's a little proof that goes back to the ancient Greeks, in fact. So suppose not. If the set of primes is not infinite, then we can list all the primes. There they are, p1 up to pn. There are no other primes except the ones in this set S. And now you may recall the trick with this is, that goes back to Euclid, is to multiply all these together and add 1. Now n is not divisible by any of the primes in this set S, because whenever you divide n by any of the primes there's a remainder of 1. So either n is prime, or it has a prime factor q, but that q can't belong to S. Then in either case we have a contradiction. And that's the end of this little section.